For the majority of this video, I want to focus on this differential equation. When the variable u in this equation is taken to represent the size of a population, and when the constants r and k are taken to be positive, this expression can be viewed as a recursive model of population growth. If we add a statement that says the population size u at time 0 is equal to a, then we're faced with an initial value problem. Although the differential equation involved in this initial value problem is nonlinear, it turns out that we have all the tools necessary to solve it. Indeed, finding an explicit solution, in other words, an explicit model for the relationship between population size and time, is the main goal of this video. Our first step toward achieving this goal is to assume that there are actually individuals inhabiting the population we're modeling. In mathematical terms, we're saying that the variable u is not equal to 0. Based on our experience in previous videos, we can see that the assumption makes mathematical sense, provided the initial size of the population A is not 0. This plot of du by dt versus u shows us that as long as we initially place a particle on some point A other than 0, it will never end up on 0. Knowing that u is non-zero for all times t is important because it allows us to define with great confidence the new variable y is equal to 1 over u. Let's now study how y changes with time by considering the derivative dy by dt. Applying the chain rule, we see that dy by dt is equal to -1 divided by u squared, all multiplied by du by dt. We can rewrite this by subbing in our expression for du by dt as we've done here in curly braces. With that done, we can tidy things up by canceling a u inside the curly braces with 1 from the denominator here, which gives us this. Bringing 1 over u inside the round brackets leads us here, which simplifies to this. Now, have a look at the expression we're left with. We have a 1 over u that is by definition equal to y. So really what we're left with is an expression that's linear in y. Amazingly, what we've done by introducing the new variable y is transform a nonlinear differential equation into a linear one. In order to complete the transformation, we'll restate the initial condition and require y at time 0 to be equal to 1 over a. So here is the current initial value problem we're faced with. It features a first-order linear differential equation. Putting the differential equation into our standard form allows us to identify our v of t function. We can now simply apply the formula we derived to state the solution to the problem in the following way. When tidied up a bit, the solution becomes this. And after evaluating the definite integral, we find the following simple expression for y of t. We can now find the solution to the original differential equation by observing that u is equal to 1 over y, and so we have this. Applying some high school algebra in a few steps, shown here, we end up with a tidy formula that shows how population size u depends on time. In keeping with previous videos, we see that as time tends to infinity, the population size tends to its equilibrium value of k. Let's now take a few moments to consider our current version of the preferred population growth model. Because this version is non-recursive, we can discuss its predictions using a plot of u versus time. Our discussion will need to make reference to the value of k, which I'll add to the vertical axis like this. If the initial value a happens to be greater than k, then the graph of u versus time looks something like this. That is to say, the population size u decays to a horizontal asymptote at height k. Alternatively, if a happens to be less than k, the graph takes on an S shape and looks something like this. Again, we see that the graph approaches the horizontal asymptote at height k over time. If a happened to be exactly equal to k, then the graph of u is simply a horizontal line that sits right on top of the asymptote. Of course, this isn't really surprising because we knew that k was an equilibrium state of our model. What this picture shows us, though, is that an equilibrium can be thought of as a rather boring function whose graph is nothing more than a horizontal line. Even though we ruled it out earlier in the video, we can circle back and think also about what would happen if a was equal to 0. If this is the case, we have another equilibrium, and again, this equilibrium could be represented as a boring function whose graph is a horizontal line, now at height 0. This illustration also gives us a different perspective on the stability, or lack thereof, of equilibria. We see that as we move to the right along the t-axis, solutions begin to look more and more like horizontal lines at height k. It's for that reason we say that k is asymptotically stable. By contrast, solutions that begin near a value of u is equal to 0 veer away from the horizontal line at that height, and it's for that reason we call 0 an unstable equilibrium. Before we wrap up, I want to take a step back and appreciate the bigger picture associated with what happened in this video. We were able to solve a nonlinear differential equation in a very clever way by introducing a new variable y. The clever trick we used is referred to as a Bernoulli substitution and can be applied to any Bernoulli equation, meaning any differential equation that can be put into the following form. It turns out that the substitution one would use to solve any Bernoulli equation depends on the constant n found within. Given n, the substitution that will work, in general, will be y set equal to the unknown function u raised to the power 1 minus n. In retrospect, you can see that our recursive model for population growth is a Bernoulli equation. And you can see that the substitution we used follows this standard recipe. It's time for a recap. In this video, we managed to solve the nonlinear differential equation that we'd used in a previous video as a model of population growth. The solution itself was achieved by transforming the nonlinear equation into a linear one, and what we did in this regard is an example of something that can be done with any differential equation that has the same Bernoulli form. Once you've mastered the ideas presented here, you'll certainly be able to solve a Bernoulli equation using a Bernoulli substitution. I also want you to be able to recognize equilibria as bona fide solutions to differential equations, even if they're solutions whose graphs are boring old horizontal lines. As always, this video is just the tip of the iceberg. Do the readings, visit the forums, and make sure to attend your tutorials. Basically, give yourself every chance to make your time in this class a great success.